basic authentication, Active Directory, LDAP, and what's wrong with it? Well, if you don't know the term basic authentication, it's actually a lot more complicated than the word basic implies. But it's complicated because it's so simple, and so simple to decrypt a basic authentication header. We've all been prompted to type our ID and password for years in these pop-up windows and haven't really even considered what the server's doing in the back end after we type in that email address and that password. And often the developer has just written some very simple code, which I'm showing at the top of the slide. And that very simple code is taking your email address and it is concatenating it with a colon and putting your password after the colon, and then it's not encrypting it, it's literally doing a base64 encoding of that information, which I'm showing here. If you're typing in user@domain.com and your password is typed in as not secret at all, because it isn't, it's sent in clear text as a base64 encoded header in the authorization header. Now, but that's okay, Ryan, if I'm using HTTPS, right? Everyone's going to say, yeah. No. Why is it not okay? Because even if HTTPS keys are not stolen, and even if the protocol is not downgraded to SSL v3, and even if there isn't a Heartbleed attack, it's still going to terminate the SSL on a web server and write that header to a log file, and then that'll be splunked by an admin who can just copy that information and decode it in a web browser in literally a half a second. There's no crypto effort at all, there's no keys involved at all, it's literally just an algorithm that's doing a cipher, Caesar cipher, where A is Z and B is Y, and T is E. It's, a 4-year-old can decode it. So, now that we know what the problem is, let's talk about, well, actually there's some more problems here. So at the bottom, I talk about LDAP and LDAP-S, and so people are going, well, I'm using LDAP-S, I'm using port 636, which is encrypted, I'm not using port 389. Isn't that better? Well, even if that is used, most tunnels that are created over 636 are not using X59 certificates. They're typically just using someone's email address and password to create that HTTPS session over port 636. So it's still very easy to sniff that traffic and to get the credentials of your Active Directory server, which are often not even used. Most Active Directory servers and LDAP servers don't even have those credentials turned on and allow anyone to search the entire directory anonymously. So you don't even now know who's connecting to your user directory because there's no prompt for the user. An LDAP search with the IP address will get you the list of every email address in your company. So now we know we've got a problem to deal with. Okay. I want to focus now next on how do we realize end-to-end security. So what I mean by end-to-end security is the desktop is now a phone, the VPN is now an LTE or 4G network, and there are no more VPNs. Even if there are VPNs, if you haven't read the news recently, the Diffie-Hellman algorithm has been breached easily because the same two prime numbers are often used repeatedly to create that tunnel. And so a clever crypto hacker that knows about prime numbers and these algorithms is typically able to just figure out how to unlock that VPN tunnel. And so that, as a result, has caused a lot of CSOs and CIOs to go, well, why do we even pay for these VPNs? Let's just use the cloud. Because the VPN's not buying us anything anyway. Okay, so that's happened, and here we are now. A lot of you are looking at your corporate email on your phone over a public telco network, and you're doing business transactions over a public telco network. And these are on shared lines, and they're broadcasting out in the world, and we can all listen to that traffic if we go to a Black Hat conference in August and stop at one of the booths and pay $2,000 for a pineapple and pretend to be an LTE tower and just be a man in the middle, and now you're connecting to someone's little box in his laptop bag, and you're not even connecting to Verizon and AT&T, but you think you are. So now we've got another problem to deal with. Pineapples are everywhere. If you go to Manhattan, you're probably not ever connecting to an actual telco tower. You're probably connecting to someone's sniffer that's pretending to be, and then it's just routing to the internet, and you think everything's fine because you're able to get your email, but so are they. Okay, now we want to secure the back end. You've all got packet capture happening. So what happens after those packets are captured and you're doing your data discovery? Who's re-encrypting that data? Who's changing the keys on the package you've captured? Who's protecting the information that's revealing all the user IDs and passwords and secrets? All right, so we've got another issue to deal with in the back end. We've got to rotate our keys. We've got to worry about the fact that keys can get stolen. And so you don't want to just count on a 2-year expiration of a certificate, even though RSA says it's going to take 2 years to crack a 2048-bit key. It's only going to take 2 minutes to use it if you steal it or pay for it. All right, now everyone's heard about IoT. I'm into IoT. I think it's a toy, so I play with IoT with my kids. I don't think it's ready for business. A lot of people are trying to make money off IoT because it's a nice new TLA that we're talking about. I'll just say buyer beware. An IoT device, like this watch here, is not a 64-bit system. It doesn't have crypto on it. It's a very low-powered system. And so you have to wonder, well, what happens if that IoT device is just out in the world sensing temperature data or sensing video feeds or sensing audio feeds, and someone just walks up to it and takes it? How much effort would they have to actually spend to get whatever data is still in memory off that device if they just happen to take it? Okay, so now there's another problem we have to deal with, putting IoT sensors out there. So I'm going to address all these issues when I talk about architecture. I just wanted to set the stage for what problems are we really trying to solve right now. And we're really trying to solve a problem of trust. And we have to ask ourselves, why do we trust what we're using? Just because it cost $1 million? Is that a reason to trust it because it was expensive? No, you really have to ask yourself, why am I trusting this? All right. So one of my favorite thinkers and engineers and idols is Buckminster Fuller. And I'm going to talk about architecture today in the context of buckyballs. So I wanted to set the stage of my architectural patterns by telling you about this amazing book I found. He wrote it in 1968. I'm walking down the street in Austin to an old bookstore for rare books. And I go into this bookstore and I see this book in the window. I'm like, oh, wow, I love Bucky. I gotta go check this book out. I've never heard about this book. And I have this book, the actual book. If you open up, you still smell the 1968 pages. And I don't just have the PDF version I'm getting a link to at the bottom. I actually have the physical real book in pristine condition. And I read it. And, you know, these are all quotes from the book, and I just love, you know, his line of thinking, where he takes his perspective, because he wrote this in the twilight of his career, you know, at the end of all of his inventions, you know, as he was just meditating and, you know, living his life. And he starts to just think about Earth in the context of, we're moving through space, this is our spaceship, and it's got finite resources, and we have to keep this thing maintained and in check, otherwise the spaceship will stop functioning and we'll run out of resources. So he's challenging us as readers of the book, how big can we think? And as planners and architects and engineers, it's really his call to action to us that he wants us to take the initiative to keep this machine in good working order, because we all really don't want it. And that's what we're here to do today. I mean, that's what we're all doing when we go to work, right? I mean, you're all trying to make the world a better place with your companies and your solutions. You know, in healthcare, you're trying to keep people healthy. In banking, you want to keep people funded so they can support themselves and their families. So we're all good people trying to actually run this machine called Earth. But why are we trusting the tools that we're using is my question today. Are they the right tools? Are they the right solutions? Do we have the right architecture? Or are we blinded by vendors that are just charging us a lot of money? So buckyballs, if you're not familiar with buckyballs, the geodesic dome, Epcot Center is an example of a buckyball, a golf ball is an example of a buckyball. But these occur naturally in nature. They're not just structures that are, you know, large. They're actually very small nanostructures as well. They just happen to evolve and form this way, and we've observed them. Carbon nanotubes are shaped like the one at the bottom, and they just happen to organize themselves this way. So I'm not going to show you the traditional network diagrams that you're used to seeing in these talks. I'm going to get you to consider how this concept of microservices will start to result in a self-organizing architecture. We have to, as architects and planners and engineers, nudge these APIs and these services in the right direction so we don't lose control of them. So the first class of microservices that I'm talking about, so this logo up there, if you're not familiar with that, that's the micrometer symbol. So when people start putting this together in front of the word services, this has become the new buzzword for APIs and what we used to call web services. You're going to hear everyone start talking about, I'm building my microservice now. And you'll start to see that symbol in front of the word service, just because it's cute. But I put the omega symbol right after it. I put the omega symbol right after it for a reason, because I'm here now talking about, we've got this brand new alpha concept, this beta technology that people are talking about out in the marketplace, these startups like Google and whoever out in the marketplace saying, I'm building microservices, look at me, Netflix, I'm building microservices, look at me, look at what I'm doing, this is great. But I'm asking the question, is it mature? And so I'm using the symbol omega next to it as, I want a maturity scale here for, well, what are these architectural patterns that we're actually out there building and deploying, and how mature are they? So the first class of services and APIs that I'll talk about, we all know what a read-only API is. For example, if you just want to get weather data, you're not able to change anything on that API. You're just able to get what is the temperature now, what are the weather conditions now. So that's what I'm putting up there in the first class. There's a class of buckyballs that are called, they're not buckyballs at all, they're really just called meshes. So we're not quite an indestructible dome yet. We're just now forming an integrated system of sensors out in the world that are connected. Temperature sensors on every doorway in the hallway, so that the air conditioner is going to turn on and off. All right, so that's relatively low risk, because it's just reading data. You're not really going to lose much money if that is hacked and compromised. You're not going to lose really any data, because everyone has access to the temperature. But what if it was sensing something that mattered? Maybe it was market-moving information on Wall Street, for example. The number of options prices that are option prices are coming in for a specific ticket right now might be something that you wouldn't want to lose control over if you're Bloomberg or Reuters. So we now have to think about what is the data that's read-only. It's not always temperature data. So think about that as we think of, well, it's low risk, but it's only low risk if the data that's being delivered is not confidential. All right, so the next class of buckyballs are known as graphite meshes. And I like that picture because now we start to get into the concept of what we used to refer to as an n-tiered architecture, where there's layers of APIs and services in different enclaves on the network. There's a layer in the DMZ, there's a layer in the application tier, there's a layer in the data tier, there's a layer in the back office processing tier, there's another layer for auditing and archiving. And so we've got these different tiers of services. Maybe in the DMZ I can only get the real-time data, but I have to go down to the archive tier to get something that's 2 years old. And so we have to think about this in terms of, well, what are we reading? How fresh is the data? And how long am I keeping the data? And where do I store it? How do I protect it? Who do I give it to? So think about layers of APIs and services. And where are going to put them on the network? Everything doesn't belong on the internet for sure. So you have to ask yourself, what does belong on the internet? And what do I put in an enclave? So I want you to remember that word and emphasize the word enclave. And then we'll talk about how to build it. The next class of meshes or self-organizing groups of things are Lonzonite meshes. And these start to look like integrated honeycombs where we have effectively A and B merged together, where there are meshes that are now, they're traversing across layers, and they're always sending information back and forth. The DMZ is always talking to the application tier, the data tier is always talking to the DMZ. And so now the risk is starting to be increased because there's now a porous network. So you'll start to get into that. After you build a layer, someone's going to go, hey, can you open up this port of the firewall? Can you let this thing talk to that thing? It'll get approved. And then it'll start to form a structure that looks like this. All right, now we're going to talk about not read-only transactions, or actually transactional APIs, or transactional microservices. What do I mean by a transactional microservice? I mean, you're moving money, you're executing an event. There's not just sensing going on, you're not just delivering information. You're now causing something to occur. And so my point here in showing this class of buckyballs is that, well, it should be stronger. If you're doing that level of risk now, you should be increasing the strength of it. And what will make it stronger is that at every ingress and egress point, there will be a policy enforcement point. You're not just doing firewalling on the edge of the network now. You must be doing policy enforcement and gateways at every single tier of your network. And as a result, it'll create trust domains that are well formed, and the only transactions that should get through are transactions that have indeed been authenticated, authorized, and audit logged. So again, bear with my metaphors and my poetry here as I show you these non-traditional network diagrams. But I'm trying to make the point about strength. The buckyball is well known in the world and in science as a strong architecture. So the next class of buckyballs is even stronger than what we typically see as a golf ball. They're called Fullerite meshes. And so I'm just saying here that, well, what would make it like a Fullerite mesh? Well, maybe it's using no spinning disk. Maybe it's only using solid state technology at this point, and all of your services have no spinning disk involved. So now we're increasing the speed of the system because solid state disk is faster, and we're probably also increasing the security of the system because erasing that information off the solid state disk would be easier than trying to find all the spinning disk that it's been replicated to. Okay, the last point I'm making is it should be able to withstand real-world harsh conditions. Maybe these things are out in the wild. They're having to withstand changes in temperature. The weather's getting colder now. These devices need to operate below freezing temperatures. And so that solid-state technology actually is required because spinning disk would stop moving at the cold temperature. You know, data centers are always 60 degrees. The real world is not. And so you'll see the introduction of solid-state technology as we put IoT devices out in the real world that have to deal with heat, cold, water, ice, and all the things that are out in the real world. And theft, that's where we go on the bottom one. So the rugby ball meshes, I'm trying to make the point that, well, what happens if this is one of my sensors, and it's over there, and Brent walks up and takes it and leaves the room? Well, on my phone, if he doesn't know my password, doesn't have my fingerprint, hasn't cut off my thumb, he's going to have a hard time getting my information because it's locked, and hopefully I've got my device set up to self-destruct after 10 failed attempts. And it should wipe itself and all the data will be deleted. So even if he did plug it into a wire and try to dump the registry or all the bits, it should by that point have been erased. And so think about that in terms of if you are doing microservices and you're dealing with maybe real confidential information, maybe it's medical devices, maybe it's a device that's sensing someone's health condition if you're working in a hospital or working with the Cleveland Clinic, which I have worked with the Cleveland Clinic in the past on pacemakers, and actually sensing data out of pacemakers. Because why are we sensing data wirelessly on pacemakers? Because they've got so many people with pacemakers that to see them physically in the office is not working enough hours in the day. So they've got an issue to keep these people alive. And pacemakers are, again, another form of IoT devices out in the world that are blurring the lines between used to be very low-risk technology, now it's very high-risk technology. There are real hazards to mitigate here. If someone DOS attacks your pacemaker and drains the battery, it's not going to have the electricity to wake you up should your heart need to beat, or to adjust your rhythm should you have a palpitation or an arrhythmia. So we really have to mitigate the security of these kinds of medical devices that are being used to keep ourselves alive and healthy. All right, so after transactional systems, where they're taking action, pumping a heart, or executing an event like moving money, what's going to happen next? Well, we'll be building completely integrated systems. The next tier of maturity, so we started out with just sensing read-only, then we went to transaction, now we're getting a little bit more mature, a little bit more sophisticated, a little bit more risky. Well, even more risky and more mature is you want to build a completely integrated system. Now, you've got two paths to go here, in my opinion. You could end up like the 1990s with a spaghetti mess of integration, which will result in chaos, impossibility to manage, you won't be able to patch it, upgrade it properly because you won't know where anything is, and you'll also introduce backdoors and holes in your architecture. It'll be such a mess. So if you don't want to end up with that, think about an integrated bucky tube, where you've got bucky balls that are actually traversing your entire network, across your company, in the United States, across the pond, into the other countries where you're doing business as well, and the entire system is organized as a structure with policy enforcement at every single enclave. Policy enforcement meaning you're checking the identity of the requester, you're checking the entitlements of that requester, what group are they in, what role do they have, what scope is on their token, should this event be allowed. You're not just allowing anonymous connections at all. Every single event is authenticated and authorized. And you're even inspecting those transactions for malicious activity to mitigate the risk that a clever person with malicious intent could take advantage of a zero-day vulnerability in the software's version you're using today, which is what we're trying to mitigate. By doing this, I'm also advocating for honeypots. Should you detect malicious activity, don't just give them a 401, don't just give them a 500, give them a nice 200 with a response that looks like it's a real success. And as a result of keep trying, and you'll get to find all the IP addresses that you're using to make that malicious request. It'll never reach the back-end database. It'll go into a fake service, a mock API, and it'll deliver XML or JSON that looks like the XML or JSON they're expecting. But it'll buy you some time to track down where they're coming from, because they might be coming from a cloud node in the UK, another cloud node in Australia, they might be on different cloud providers, someone's on Amazon, someone's on Azure, someone's on Rackspace, who knows where the bot is running. It's probably not a human at all, it's probably a program that's just been deployed. Okay, now an enclave, which is what I'm showing there as the fully integrated mesh that we finally got to when we built it. We've got a real business system here and it's mature. We've done our work as engineers and architects, and we've put the policy enforcement points in place. And that's what I'm showing you here. What is a policy enforcement point? Well, it's beyond a firewall. A firewall does open port 80, open 443, and then great, the hacker comes into 443. Doesn't really buy you much. An API gateway is doing much more than that. An API gateway is going all the way up to layer 7, looking at the envelope of the message, looking at the contents of the body, looking at every single header, looking at the parameters in the REST GET URL, looking at the query parameters, the path parameters. If the parameter for account number happens to look like escape character select star from table name, that should be caught by the API gateway. The SQL injection detection policy will see that that doesn't look like an account number at all. I was expecting an integer that was 7 digits long, and that's got an escape character with a SQL query on it. And, well, I should not let that go to the back-end database, because if I do, that'll dump the database, which is how 85% of data loss occurs. Is the front door is used to get to the back door because you didn't see the SQL injection come right through the front door with all the other requests. So put the API gateways in place with policies on the API to detect that the parameters in those APIs that you're exposing might contain data that is not expected. This is called input validation. One of the most mature things you can do as engineers is check to see that the data coming in is actually the data you expect to come in. Don't just let any data come in. And that's where an API gateway comes in, because the firewall's not going to look at that, load balancer's not going to look at that. So you've got to have something that understands the schema of the message that's coming in. If it's SOAP, it has to understand the namespace of the message. It has to be able to XPath the message, or JSON pass the message, if it's JSON data. And API gateways have that ability. It has the logic because it knows the WSDL for the service, or it knows the Swagger for the API. And so it has the message definition that's expected. It has the data types that are expected. The serialization is defined in the RAML. This operation should be serialized as application JSON. This operation should be serialized as application XML with namespace foo, whatever the namespace is. So because the gateway has this information about the API, it's able to determine that the data coming in doesn't match what's expected. So the hacker would have to be pretty clever to get through that. I don't think they are. I think they're robots. All right, the next level of architecture to consider is what I like to call cloud as a DMZ. And this is where we're offering another buffer protection for your DMZ. I'm not saying get rid of your DMZ. I'm saying put a tier of API gateways on the edge of the internet in a public cloud And so if you happen to need to do business with the public internet so that you can accept connections from phones or laptops that are connected on Wi-Fi networks in coffee shops, that those connections are first filtered by the cloud. That way the DOS attack and the botnets don't go to your DMZ and your front door, they go to the cloud provider's front door. Now Amazon's supercomputer has to deal with the botnet, not your firewalls and switches and routers and servers. So leverage the cloud as a buffer of protection to reduce the attack vector of what comes into your door. Hope this makes sense. The idea is that this tier of gateways in the cloud DMZ, so let's say that this is your VPC on Amazon or your cage at some colo center. It's not your data center at all, it's someone else's network and someone else's rack and stack and power and all that. That these gateways are only doing authentication and identity verification, so that way we never deal with the anonymous guy that has the bots that are just trying to guess passwords or steal credentials and try to come into your system. So the idea is that all the anonymous activity should be stopped here, at the edge of the network, as soon as we leave the Wi-Fi network and touch the service provider. And then the only connections, these are mutual TLS tunnels, the red lines. So what I'm saying here is that the gateway that you deploy in your DMZ should only be accepting connections from a gateway that has certificates on it that it trusts. And those certificates should be used to encrypt the tunnel. And so the HTTP session from here to here is a key check on this side and a key check on this side. This guy says, yeah, I know your keys, I trust those keys. Those are new keys, I just gave them to you a month ago, they're not old keys. Great, they haven't expired. And this guy does the same thing. Yeah, you really are you, you're not someone pretending to be you. You're not a man in the middle that's got old keys that have been stolen. Right, so you're checking certificates on both sides. That's what we call mutual TLS, as opposed to just SSL. Where SSL, the way we've been doing it in the past, the browser would just go here and say, yep, you're really the website I'm expecting to see, you're not a phishing site. So that's all it was doing in the past, was telling us it wasn't a phisher, pretending to be the real .com. All right, so on the API gateway, what's possible? Well, what's possible is declarative configuration of really hard stuff. And what I mean by that is declarative means we've already done the QA, the coding, the debugging of the rule, the code exists. No one is sitting off in a cubicle writing new Python or Java code. No one has to send that code into the change management system to be debugged and QA'd and tested, because how long does that take to build something brand new and to get it certified as ready for production? Right? That's a multiple week process. So if we're really going to manage this process, we have to get into the business of there are no more emergency changes, there's no more custom code, there's no more uncertainty about what's actually been built by the developer and how good it was. There's no more, I need to pen test this first because that's expensive and time consuming. If we're going to patch a 0-day with a change, we're patching a 0-day with a change with a solution that has been verified, that has already been pen tested. It doesn't have to go through another QA process, because if it did, the 0-day is not going to get patched for weeks. So these policies ship with our API gateway. They're out of the box. They're configurable by a non-programmer. You don't have to be a hacker either. You don't have to be an expert either. You have to have some education. You have to have used it a couple times. You have to know the concepts. But it's a UI with fields on it, and it's a wizard-based approach, and a help button at the bottom when you get lost, and a support desk to support you, and professional services people to guide you. Because it's not brand new, and I don't have to say, tell me the code and let me spend a week with you to figure out what you wrote. I don't really want to do that. I'm busy. So, examples of policies: OpenID connections, the ability to do OAuth tokens, the ability to verify the application identity of the consumer. It is a trusted endpoint that we know. The ability to do cross-origin resource sharing, so I'm only doing business with other .coms that I have an affiliation with. I'm not allowing just anyone to talk to me. And I'm not just talking to anyone when I have to do redirects. You really want to do it, but I don't recommend it. Mutual SSL basic authentication, we really do. We don't call it SSL anymore, that's an old acronym. It's now called TLS. SAML's still around. If you've got SOAP services, you probably have a need for SAML tokens. SAML tokens are all like OAuth tokens.
except they're XML and they get inserted inside the envelope of the sub-message. So we've got policies out of the box that can take an OAuth token, the subject out of that token, the email address out of the token, and use OAuth on the front side with the mobile app, and let the gateway take that email address and inject it as a subject in the SAML token, and then pass the identity of the user to the backend server. So now you know the identity of the user, and you're transforming that identity into the token format needed by the old legacy SOAP service. Because you will be taking old SOAP services and using gateways to turn them into new REST APIs so that mobile apps can read them as JSON, because mobile apps really don't want to look at XML data. Because it's too costly, CPU intensive, and it's ugly. WS Trust, WS Security Transport Bindings, username tokens, message encryption, signature verification. These are all things you want to do. I'm saying you've got policies. You're literally going to configure a policy once, save it as a reusable object in the policy administration point, and then click a button to say, I want to do signature verification on these 10 APIs in production always. Now you've got a 5-minute job to do something complicated. You're going to integrate with identity providers. API gateways know about multiple identity provider protocols. SiteMinder, RSA, Oracle Access Manager, Active Directory, LDAP, Kerberos, OpenID, OpenID Connect right now. And OpenID Connect is my new favorite, and it should be something you look at if you haven't looked at OpenID Connect, because it's much simpler to configure than LDAP and all these other ones. It's got a URL, and the URL returns all the configuration parameters, and so now you don't have to hire an expensive consultant. It actually configures itself properly. Denial of service attack prevention, we definitely want to do that. We want to check to see that the data coming in doesn't have a SQL injection, so we're not dumping the database to a normal user. We want to scan, if we are accepting attachments, we want to make sure that those attachments don't have viruses on them. Well, you can integrate the API gateway with your existing Symantec and your McAfee servers using an ICAP protocol. Open standards-based protocol to get the gateway to say, send my attachments over to my existing antivirus server, and now my virus definitions that I've just downloaded and updated from Intel or Symantec, those are used to check to see that what's coming into the gateway, what's coming into the API, isn't malicious, doesn't have a virus on it. If it does, it'll strip it, quarantine it, or reject it entirely. Check to see that the schema is well formed. Don't just allow any data to come in. Verify the namespace is well structured. Look for other malicious patterns, cross-site scripting patterns, for example. Throttle the connections on a user basis or an application basis. Give different levels of service to different consumers. Debbie perhaps gets 10 transactions a minute. Brett might get 1,000 transactions per second. He's got a production license, so he's got a greater throughput than Debbie does. She's only got a sandbox license. So the gateway can give different throttles to different consumers based on their profile, based on the contract that they're using, based on the license that they're using on that API. Lastly, PKI, you're definitely going to want PKI in your system. Check to see the search is still valid, they haven't expired, that they're signed, the serial numbers match, and they're pinned appropriately to the domain you're talking to. Okay, so now we've talked about architecture, we've talked about policies and gateways, we get tiering and layers and enclaves. Now let's talk about token-based authentication. The subject of the title, I definitely promised I was going to dive deep into token-based authentication and how to solve this problem I put on the screen at the beginning of the slide, which was don't use basic auth anymore, right? So now we all agree we're not doing basic auth because it's so easy to decrypt it because it's not encrypted at all. So we want to do tokens. Why do we want to do tokens? Because tokens are not decryptable. They're a random number, they're a random hash, and they live for seconds, hopefully. Facebook and Google and Twitter and all those guys have your token living for months. That's why you never see the prompt to type your password again. But as a business system, you wouldn't do that. You would have your high-risk APIs expire tokens after seconds. If you're doing a transaction at a bank that's over $5,000, you log into your mobile app, you get a token, that token expires after the appropriate window of time for the user to fill out the amount, where it's going to, the account number, maybe it lives for 2 minutes. And then the token expires and they have to log in again to do another $5,000 transaction. So that's what I mean by tokens. It's got a limited lifespan, it's got a limited scope, and if you do steal it, and you look at it, it's just a number. You can't get an email address from it, you can't get a password from it. There's no information in it at all. So what types of tokens are there in OAuth? OAuth 2.0 right now has 4 types of tokens and 2 patterns. The two patterns are called three-legged and two-legged. Well, what does that mean? Right? That sounds kind of obscure and abstract. Well, think of two-legged as there's an A and a B, a client and a server. Okay, we all get that. That's how things have worked for a while. So with two-legged, the app ID and the secret of the app that you got from the App Store is checked. Okay, that's the app I trust. Now, the app tells me to log in. I type my email address and my password. So all four parameters are sent in that one hop. So when I log in and say I want to do this, all four parameters are sent in the one hop. Two legs. There's no redirect, there's no pop-up that occurs. That's what two-legged means. So if you are a man in the middle, and you did hack the protocol, or you did steal the keys, you now have the ID and the secret and the username and the password with one sniff. Or if you've got packet capture, that's all in one log entry. All right, so we're clear on what two-legged is. So easier to log and sniff. Client credentials does not check the user ID and password at all. It's only authenticating to see that the app is trusted. So that's what client credentials means. I trust that this client application is the client application from the App Store. That's all client credentials is checking, is that the app is the app you expect it to be. So, people use it when there's no user. So these headless devices, IoT sensors like temperature thermostats, are likely using client credentials because there's no user to type in an ID and a password. So now you've got that on your mind. Great. My favorite is authorization code three-legged. Because implicit grant, as I say, I'm not a fan, there are no refresh tokens, and because the access token is included in the redirection URI, it's again easier to sniff and be used as a replay attack. Now I'll talk about how to mitigate replay attacks on tokens in a minute. First, I'll distinguish what is an authorization code grant. So what happens in an authorization code grant is the app is going to connect to the service. The app's going to connect to the API, and the API is going to say, this API requires an OAuth token, so begin the, you'll hear hackers and engineers talk about the OAuth dance. Begin the OAuth dance. And so it'll prompt for an authorization code, which means give me your client ID, which means give me your app ID, or whatever's been used in the App Store to identify the app. So that only starts the process. It says you are an app that I trust that is permitted to even ask for authentication. Now I'm going to redirect to another site. I'm going to redirect you to another site, and that site's going to check the ID and the password of the user of the app. So that's the third leg. That redirection, that pop-up that occurs is why it's called three-legged. Because that other site doesn't need to be the same .com domain name. It doesn't need to be the same server as the API server. So I like this. Because now you've got to have a sniffer on here, the service, the API, the microservice, and you'd have to have another sniffer on the identity provider, the OpenID Connect provider, in order to get both sets of credentials. So it's harder to intercept. So different types of tokens. Bearer tokens are the beginning, that's just a random number. Refresh tokens live longer. They're used to get another token when the bearer token expires, so the user doesn't have to type their password again, so use that for low-risk transactions like the read-only sensors we talked about at the beginning. And then for the high-risk transactions, MAC tokens, MAC is short for HMAC, hash message authentication code. And so that is great to prevent the man-in-the-middle stealing of a token and reusing of a token, or someone taking the token out of a log file and trying to replay it, because the nonce has been expired on the first transaction. A nonce is a number that's usable only once, so once the success goes in, the database goes, this token's already been used. If they try to get used again, you should log an alert and find out who did that, because that shouldn't happen. So what does this look like in the real world? Authorization here looks like this. This is a bearer token example. Just a random hash, you can't decode it, you can't decrypt it. That comes in, great. It's okay, the API gateway says you've got a valid token, success, here's your data. Scoping API operations is where we go next with tokens. Every token is not equal. Some tokens will have only a public scope. The low-risk operations are API, like give me the status of the service, low risk. Anyone can do that, make that public. But delete something, we're going to give that a private scope. You must have a license. We must know that you are who you are in order to do this. And so we're going to check the credentials of the token. So you'll have scopes of different types on your API, and you'll check the scope before sending the response, or before even letting it leave the API gateway and going to the API. So it'll be stopped on the edge of the network. So what does this look like? I've got a valid token now, but I'm trying to do delete. I put a value in there, I'm just trying to guess a number, 1, 2, 3, maybe that's a real device ID, I might get lucky. You don't have permission to do that, 403 forbidden, right? Because you don't have a public scope token. So the gateway stops it, it never leaves the edge of the network. This is what I mean about creating this nanotube structure. Every single point where you've got a service listening for serving something, you're checking token validity, identity entitlements, and you're giving 200s only when necessary and 403s and 401s when it's inappropriate. Now we can do things like also, we know the identity of the user, we can enforce different thralls for different identities because each identity is linked to a contract and a license, and so they'll have different permissions. And so this is an example of, he's trying to DOS attack me, he's sending just too much traffic. I only want him doing 10 transactions a minute. He's just sent a load runner at me and he's doing 1,000 transactions in a minute. I got to stop that. And now he gets, you've exceeded the SLA. It never leaves the DMZ, it never leaves the gateway. It doesn't take the back-end service out of service because it stopped at the edge of the network. So you're now, again, reducing the impact on your system by putting these gateways at the edge of your network. Putting it all together, you'll have an architecture that eventually looks like this, where you'll have gateways on the edge and developer portals on the edge that people can use to identify themselves and request identities. They'll type their email address, they'll say, give me an app ID, I want to build this iPhone app. That'll then be used to actually do business with the back end. And you'll have a sandbox. Here's my sandbox over there. You'll have a sandbox identity provider for your developers to use and your testers to use. And they'll never ever connect to the actual identity provider for the real employees and partners and users of the system. That's only used for the production system. So you're now segmenting identity systems for different environments as well. I'm going to use the remaining time I have. I've got 10 more minutes. Let's just go into some concepts. Since you've got me here, I'll just relay to you some of the information I have on how this OAuth dance works, because it is kind of elusive and I don't want you to have to read it alone. I'll just talk you through it. The parameters to get a token are, you'll get a client ID, there'll be a redirect to URI, you'll get a response type, the scope you're requesting, public or private, and the state of the system. It'll give you a response, which is a code. The code is just a number to get the token. So that's the answer that we know you, we trust you, and now you can use that code that's going to live for just a few seconds to ask for a real token. Okay, great, it looks like that. Meaningless, and it is going to go away quickly. And you can't use it to do business with the API. It's only a code to get a token. Now you've got the code. The code is a parameter in the request for token that's being sent in as a post to the token URL. The OAuth token URL is posting in that code. He's saying, great, you know me now, give me the token so I can use your API. Awesome. Here's your token. That's what we inserted in the authorization header. That's the dance. That's the back and forth that occurs. And then the request comes in. There's your authorization header for whatever API call is being made. OpenID Connect. The basics of OpenID Connect are, it's an emerging standard that's replacing LDAP integration. So OAuth can be integrated with your LDAP and Active Directory. Sure, we do it all the time. I just don't think it's the best thing lately. It's hard to do and it's hard to secure. So what's an alternative? OpenID Connect is a nice alternative. It's got this well-known URL for configuration. It tells you how to configure it itself, so you'll effectively point your API gateway, OAuth domain to this OpenID Connect provider URL. It's going to reply with the other URLs needed to get tokens. It's going to tell you how to talk to it. So there's a configuration URL that replies with the answers for how to set up your server. That's why I like it, because it's actually simplifying configuration. It's stopping you from forgetting to type, that slash at the end. Oops, I left that off. Or I left the JWKS part off, or I typed it wrong, I fat fingered it, right? So it's actually preventing human errors. It looks like this. When you talk to the well-known configuration URL, it's going to provide an answer in JSON format that says, these are the grant types I support, and only those grant types. So you're only allowed to ask for those types of grants. And these are the scopes that I'm going to give you back. You can use any of those scopes and you can link them to your API. Would you like to use me? Absolutely, this is easy. So configuring it in the system, you're now going to set up your OAuth binder. What grant types do you want to support? Oh, I don't want to do any two-legged at all. Let's uncheck that stuff. Matter of fact, I don't want to do implicit grant. Let's uncheck that too. I only want to do this one, and I want to reduce that timeout from 600 seconds to maybe 10 seconds for this use case. And so you can adjust all those timeouts. Again, you're not a hacker here. You're not a programmer. You're literally filling out a form on a web page. You then select the scopes you want to use for your system, and then how you're going to sign it, what algorithm you're going to use, SHA-256 with RSA. You're going to then configure the scopes and then link your scopes to your API operations, which one's public, which one's private, when do I use email. And you might enrich your tokens for multi-factor authentication for fraud detection. Don't just check that the guy knew his OpenID Connect password and his user ID because someone might have stolen that or guessed it. So how do I do fraud analysis now? Well, you can enrich your token with properties on the token, and you can ask them before they get their token to also, in the pop-up, type in their account number that they know, their employee ID, and the SMS code they just got on their phone. So I really know this is the person who claims to be the guy that knows that ID and password. And now, as the API request comes in with this token, you can check those parameters before just saying, here's your data, or yeah, I moved that money. And if those are not valid and linked to that user, then you could trigger an alert and do some analysis on who sent that in with the wrong information, and was it just a mistake? There's another token that's emerging I'll talk about briefly, which are called JOT tokens. They're spelled J-W-T, but they're pronounced J-O-T. That's how we do things. RFC 7519, if you want to read about it. In short, there's an easy tool on the website, jot.io, will get you quick started. Beware of this parameter. Algorithm is none. For some reason, it's in the spec. And we're all working to get it out of the spec right now because it poses a nice risk. So we're actually saying, why did you do that? And that doesn't make any sense, and stop it. It should only be this, hash 256. So again, beware of emerging technology, new technology. You don't know what these guys are doing when they write down these specs, and you hope that they're smart enough, but maybe it's a mistake, or maybe it's, who knows what it is. This tool, jot.io, will actually encode and decode your tokens and render the information as JSON for you so you can see what's inside the JOT token. The only reason JOT tokens are interesting are for exchanging information. They're a little bit more transparent than a normal OAuth token is. And what I mean by that is back from the OAuth server, when you get a JOT token, you're also getting a lot of information about who owns that token. And people are using these tokens to say, well, I logged on to my social networking site and I want to use that token to do business with my Salesforce site. And I want to send them all the information about who just logged on in the JOT token. Well, now they're sending personally identifiable information across the network between two different domains. And I go, well, I get why you want to do it, but I don't know that you really want to do it on the internet. Maybe you want to do it in an enclave between two business systems. But I don't really think you want to do it on the internet. Because now all your users are being put at risk. So it's going to have this information to respond. Who the issuer was, the subject to the user, which is another word for email address or user ID. Subject is synonymous with user ID. The intended audience of this token should be, business system A, business system B, the SAP CRM system, or whatever the business system. That's the audience. When it expires, issued at, authentication time, nonce, that's usable only once. You'll then get some token claim information, class references, method references, authorized party. Then we get into a little bit more level of detail about who this user is, maybe their login hint. Why are we sending that? Salesforce. User info, claim specs, and then we got all the stuff that we would expect to see that reveals the user's information. Their address, their name, the birth date, these X509 directory properties that are already in your LDAP database today. So those are being stuck in these tokens now, the new JOT tokens are sending this information around. And I'll just wrap up with, may your 2016 be filled with 0 days as you deprecate this year. So I wish you a happy deprecation in December as you turn off what needs not be on. And I wish you 0 days in 2016. Happy Halloween.